Okay, so in this video I want to show you how the standard normal distribution can also be used to approximate the binomial distribution. And when we worked with the binomial distribution, we have already seen that whenever we have a large number of experiments or trials, the distribution looks very normal. And whenever certain conditions are met, we can actually get very similar results, like the binomial distribution result, which is of course mathematically the exact result whenever we deal with a binomially distributed variable. But we can also reasonably approximate the results of a binomial distribution with the standard normal distribution, and specifically when two conditions are met. So if you remember, in a Bernoulli experiment we have only two outcomes, success and failure, and if the number of trials times the success probability P is equal to 5 or greater, and so both conditions must be met, and the number of trials times the failure probability is also greater than 5, then we can use the standard normal approximation to the binomial, and then we get then very similar results. So, and I want to illustrate that using the example that we flip a coin 100 times. And then we already know that this distribution has an expected value of, let's say, heads of 50. So the mean of that binomial distribution, the expected frequency, is the number of trials times the success probability. So that would be 50. And the standard deviation of the binomially distributed variable is the square root of the number of trials times the success probability times the failure probability, which in the example of 100 coin flips would be 100 times 0.5, that's 50, another 0.5, that's 25, square root of 25 is 5. So the standard normal distribution, the standard deviation is then 5. And we can see that both conditions are, for using the normal approximations, they are met, because n times p, that's 50, and n times 1 minus p, that's also 50, which is far above 50. So here again you see the binomial distribution, and you see that the expected value, the mean, is 50. So in other words, if I flip a coin 100 times, but I do that for 1,000,000 times, the most likely outcome that I will get is 50 heads. But it could be that I get 60, 70, 80 heads. Theoretically, you could get even 100 heads. But this is, again, the correct distribution. And we want to know, so that's the problem, we want to know what's the probability that we can get 60 or more. I think that's the problem. And so let me quickly see where that is. So 105, 50, doesn't actually say anywhere what we try to approximate. Oh, here, what we try to find is the probability that we get 60 or more heads in 100 coin tosses. Okay, so let's do that first, using again the mathematically accurate distribution. And so we have the number of successes when you flip a coin 100 times. Well, when you flip a coin 100 times, I can get 0 heads or I can get 100 heads. So I create quickly a column that goes from 0 to 100. So we go again, home, edit, fill, series, step value 1, step value 100. Okay, so now what's the probability? So if you remember, for this we use the formula binom, and then it says binom dist, and then it says the number of successes. Well, that's 0, it's a very small probability. The number of trials, 100. The success probability is 0.5, and we don't want it cumulatively because I want to show the probability for getting exact 0, an exact 1, exact 2, and so on. So I put in here a 0. And then we should see something which looks nicely normally distributed. So let's copy down that formula and let's maybe format the cells and give it a number, but then we need a lot of decimals obviously. So you see that the probability of getting 0 successes, 0 heads in 100 coin flips, that's for a long time 0.000. But let's take a look at the probability distribution. Let's highlight the data array, insert recommended chart, and here we have the actual distribution, and you see that looks pretty much like a normal distribution. And what we want to know is we want to know the probability that we get 60 or more. Okay, so now we can do two things. We can go to the number of successes. We go to 60. And now we just sum up what's the probability that we get 60 or 61 or 62. That would be the cumulative one. And then down here, maybe we can see if I pushed it up. So the probability is 0.0284. Okay. So to be more accurate, let's just say here, the probability that we get successes of 60 or more. Okay, I can write that either as the sum of the probability that I get 60 or 61 or 62, and I sum them up. That's what I do first. So I go to the 60 all the way to 100 and I sum it up, and I get 0.0284, but let's remove some of the decimals. I think that's good enough. But of course, what you would do is you would use the formula, and now we would say what's the probability. So now we will say binom dot dist. Okay, so if I want 60 or more, I have to say the number of successes is actually 59. And again, because the formula binom dist, if you enter the number of successes and you do it cumulatively, you get everything up to that number. So we have here 59, the number of trials is 100, success probability is 0.5, and now I want it to be cumulatively. But this formula gives me what's the probability that when you flip the coin 100 times that you get no head, one head, two heads, all the way up to 59 heads. But because I want to know what's the probability that I get 60 or more, I need to subtract this from 1. And now we should get also the same value. And of course that would be the correct way of doing it. So in other words, the mathematically correct way of getting 60 or more heads and 100 coin flips is to use what I just showed you now. And the accurate probability is 2.84%. Okay, but now we use the standard normal distribution to approximate that. So, okay, so to get some space, I just quickly delete that graph and I delete this result. And the first probability that I showed you was the binomial. But now I use the normal distribution. The normal. And the normal distribution has, as we said earlier, we know that our data where was it? Here has a mean of 50 and a standard deviation of 5. So now I want to draw in Excel a normal distribution with mean 50 and a standard deviation of 5. So let's go back to Excel. The way to do that is now to use the formula norm.dist, not sdist. Norm.dist, open parentheses, and then you see Excel wants to know, okay, this 0 comes from a distribution with what mean? So now we enter 50. And what's the standard deviation? Well, that's 5. And again, we don't want it cumulatively because we want to see the actual distribution. Okay, so now we get this value and we can just download it again. So this is the normal distribution. That's the approximation. Okay, so now we can display both. And what I do is I just copy first the format. Okay, we have all those zeros, but now we can display both. Insert, recommended chart, and I think let's take this one here. And you see that there's barely any difference. I mean, you can not detect a difference. They are literally the same. Maybe there's a little bit of a difference if you zoom in, but it would be very difficult to identify a difference here. So you can see that the normal distribution, which is the orange, completely overlaps with the binomial. There's actually a typo in there. Okay, so that suggests that we can actually use the binomial to approximate. That actually shows that we can use the normal to approximate the binomial. Okay, so what I want to do is I want to find the area to the right of the value of 60. Okay, so 60 is here, and I want to know what's the probability here to the right using the standard normal. So step one is to say, okay, how many standard deviations is a 60 away from a hypothetical mean, or not from a mean of 50? So that's the mean of 50. Well, we know that the standard deviation of a binomial distribution, we said that was n times the success probability times the failure probability, and that we got 5. The mean, the expected value is 50 heads. So then our z-score is the 60 minus the mean of 50 divided by the standard deviation of 5, and we get 2. So now I need to get the area to the right of 2. Okay, so the area to the right of 2, so we can go here to a z-table, and you can see that in a z-table we typically get the area to the left of a z-score. So here we have 0.9772. So that means that the area to the left of 60, that should be 0.9772, and the area to the right, okay, so now it's getting a little bit tight here, so maybe I squeeze it in here. So now we could say that the probability is 1 minus 0.9772, and now we get 0.0228. Okay, so this is when we use the binomial approximation. We could also have said, so we can actually, okay, so we could also have used the formula equals norm S dist. Okay, whenever I want to know the area to the right of 2, well, that is the same as the area to the left of -2. So I can also say -2, and now I want it cumulative because I want the entire area. Okay, and that is the same value. Okay, so this is what we get if we use the normal approximation. So that we would say there's a 2.28% probability of getting 60 or more heads when you flip a coin 100 times. But remember, the mathematically correct was using the binomial distribution. And here we would say this is equal to binom.dist, the number of successes. Okay, we say 59. Number of trials, we said 100. Success probability 0.5. Cumulative, yes. And this needs to be subtracted from 1. So now when I press enter, you see the mathematically correct result, which is 0.284. Okay. So how big is the difference? So it looks like that the normal approximation is roughly, yeah, it's like 21%. That sounds like a lot, but like roughly 20% deviation, but in absolute terms the difference is 0.0057 percentage points. So it is a very good approximation. Okay, so Let's go back again to the slide. So we started out with introducing the conditions that needs to be met. N times P needs to be greater than 5, and N times the failure probability needs to be 5 or greater. Then we looked again at what the real binomial distribution would look like, and we can see that it looks pretty much like a normal. Then we used the Excel command norm.dist with a mean of 5 and a standard deviation with a mean of 50 and a standard deviation of 5. And technically the formula that I entered in Excel, norm.dist with a mean of 50 and a standard deviation of 5, basically uses that formula here. So theoretically we could have also entered that formula. We would get the same as norm.dist. And then we see that they look very similar, and in Excel I showed you that they actually overlap pretty well. Then we identified the z-score. We asked the question, okay, if I want to know what's the probability to get 60 or more, then I need to ask how many standard deviations is that away above the mean of 50, and that is 2. So we see that, and then we use the formula norm s.dist. Then we can either subtract this from 1, or we use norm s.dist for -2. That's the same result then. And this is what it looks like if you want to look at it graphically. So we have here the probability, and again we want to know what's the probability of getting 60 heads or more. Well, that corresponds to a z-score of 2, and the corresponding area to the right is some 2.2%. Okay, so let's just stop here, and then beginning with the next video, maybe let's review again and do some problem sets.